So let's talk about the universal law of gravitational. So Sir Isaac Newton in 16th century sometime was sitting under an apple tree, and one day an apple supposedly fell and hit him. That's when Sir Isaac Newton came up with the theory of gravity. Gravity is a force that holds all objects down to the earth and keeps us from floating away into the atmosphere. His theory is important because we now know what keeps us from floating into the sky. Note, people were not floating up anyway because he didn't find this law, but we know now why they were not floating up. Newton's law of gravitation, as he wrote it, it says that every point mass attracts every other point by a force pointing along the intersection of both points. The force is proportional to the product of the two masses and inversely proportional to the square of the distance between them. Okay, where F is the magnitude of the gravitational force between the 2 point masses, G is a gravitational constant, M1 and M2 are the masses of each object, and R is the distance between their centers. So Newton's law of gravitational is written as Gm, m for any mass on Earth divided by r squared, and F equals mg. This implies small g, which is acceleration due to gravity, is equals to g, the big M, over r squared. That means gravitational acceleration depends inversely on the square of the distance, and it depends on the mass of the planet. Nominally, for Earth, g is given by 9.81 meters per second squared. At the equator, g is about 9.78, and then at the poles, it's 9.83. Gravity on the moon is 1/6 that of the Earth. So g, which is acceleration due to gravity, varies with altitude. So on the Earth's surface, normally, we can say that the acceleration due to gravity is about 9.83. At 10 kilometers above the Earth, which is the normal altitude for the airplanes, the gravitational pull reduces to 9.81. At the top of the atmosphere, which is about 100 kilometers or thereabout, the acceleration due to gravity becomes 9.53. At 400 kilometers above the surface of the Earth, which is about where the space shuttle orbits, it's about 8.7. The communication satellites orbit around 35,000 kilometers, at which point the gravitational acceleration reduces down to 0.25. And moon that orbits around the surface of the Earth, the gravitational pull is 0.0. The acceleration due to gravity is about 0.027. And at which point the gravitational pull of the moon will overtake any acceleration that the Earth will probably have. So now let's do an example. Calculate the magnitude of gravitational force exerted on a cantaloupe of mass m on the surface of the Earth due to the Earth, the moon, and the sun. Knowing the mass of the Earth, the mass of the sun, the radius of the Earth, the radius of the sun, the radius of the moon, the distance from the Earth to the moon, and the distance from the Earth to the sun. Okay, let's do that. So let's do the first one. So it's asking us to calculate the magnitude of the gravitational force exerted on the cantaloupe of mass 1 kilogram due to the Earth. So if we were to find the mass exerted, the force exerted by the Earth onto the cantaloupe, it is going to be given by this formula, which is mg, where m is the mass of the cantaloupe, which is 1 kilogram, divided by the acceleration on which is 9.8, which gives us 9.8 newtons. Okay, so that's the answer to part A. Part B, it says what is the force exerted by the moon. So if I was to find what the force exerted by the moon would be, it will be g m of the cantaloupe times m of the moon divided by r squared, right? So given that this is going to be 6.67 times 10 to the minus 11, and you can figure out what the units are, where the mass of the cantaloupe is 1 kilogram, and the mass of the moon is 4.36 times 10 to the 22 kilograms, right? Is that what it is? Mass of the moon divided by r squared, which is the radius away, which is 3.82 times 10 to the 8 meters. Solve this and come up with an answer. I think my answer is 3.36 times 10 to the minus 5 Newton, which is a tiny, 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 tiny force. right? But make sure that I actually did this correctly, okay? Part C is the force exerted by the sun. So I'm going to call it the sun, and I'm going to call this one the moon, which is going to be the same mass of the moon, mass of the sun, mass of the cantaloupe, times r squared. And all you have to do is get those values, plug it in here, and solve. So I get 5.9 times 10 to the minus 3 newtons. Okay? Which is also very, very tiny, even though the mass of the sun is huge, but the distance that the distance between the cantaloupe and the sun is going to be huge as well.